give me a minute. Okay. So the main issue in additive manufacturing is the title itself. Just give me a minute. Yeah. If you see, the title was so well selected, additive manufacturing. Every one of us know it. But lab scale to field scale or industrial scale, this particular route is not that simple. I mean, like, let me tell you, whenever we open any book on additive manufacturing, there will be, nice statements saying that, it can manufacture anything. But the moment you start working with, metals and metal-based additive manufacturing, you will see that it's not a straight forward route, and you will encounter a lot of challenges. I mean, like, even if I want to deposit a, simple wall of 8 mm thick and let us say 20 mm in height, okay, it's not that simple. There is no straightforward way for it, and it takes years of research to simply just build a wall. Let me believe. I mean, like, believe me. Okay, so that is what we were trying to do from last 1.5 years or 2 years. So here you can see what are the studies we are doing. So all the studies, like, we started from very fundamental, where we are looking at how the laser is interacting with this material. That is what we felt is more important. And then we went into the depositions, and then deposition on the component level. So I will try to just take you through all these things. Okay, first we will try to understand what is additive manufacturing, especially the directed energy deposition process. I will not talk much about powder bed fusion process. I will be mainly focusing on directed energy deposition process. And then we will try to see what are the process parameters. All of us know laser power, scan speed, powder mass flow rate. These are the process parameters. But there are certain other process parameters as well, like carrier gas flow rate. We will try to see how it's going to affect. It is not going to give or input any energy into the process, but it will have a significant effect on the deposition. And now, why we are looking at process parameters when our topic is real-time monitoring? Because unless otherwise you understand the effect of each parameter individually, you won't be able to understand which parameter to be controlled under which circumstances. So typically we will see in most of the cases, people say that I will control laser power to control the heat input, but that is not the only parameter which you need to control. Sometimes you will see the standoff distance plays a major role. I mean, like, there is no need to touch these two. Rather than just by touching SOD, you can rectify a lot of errors that occur in additive manufacturing. So it is very vital to understand what are the effects of individual process parameters, and then depending upon the problem you are facing, you are going to do the real-time monitoring and control that particular parameter only without touching everything else. Okay, because we need to understand that additive manufacturing typically has a large number of process parameters, not only from the laser perspective, like what is the spot diameter, what is the Rayleigh range, what is the velocity, mass flow rate, carrier gas flow rate, powder particle size, distribution, the way it is getting focused, the velocity of a powder particle. So if you keep on talking, the number of parameters are, they cross like 30, 40. And now we cannot optimize all these process parameters. That is one major challenge in, once again, in additive manufacturing. So in order to bring this component from lab scale to field scale, instead of controlling each of these process parameters, we need some monitoring system, and we need to control some process parameters such that the component is finally deposited. So this would be the target of this particular lecture. So we will try to see the process from the process perspective. Then we will try to see the challenges in additive manufacturing and how we can overcome those challenges. Okay, yeah, like I said, can I minimize this? Dr. Subbu?
Yeah, yes, please, sir.
Is there any way that I can minimize this tab here?
No, I'm not seeing anything. We are able to see only your PPT only. I'm not
Okay,
seeing any.
fine. Then it is fine. Then it is fine. Okay.
I'm not seeing any extra thing. Yeah.
Yeah, then it is okay. Perfectly fine. So
Okay,
now if you see, I kept one statement over here about additive manufacturing. That is bringing imagination to reality, breaking the limits of manufacturability. So this is what most of us think when we think of additive manufacturing, because nowadays when we search over the internet about additive manufacturing, you will see all kind of complex components being made. But how much it is true? I mean, like, is that so simple? Even, I mean, like, you talk about powder bed fusion process. So people think it is very easy to deposit a component on that, but we need to understand that the system, the powder bed fusion system that comes, okay, with the license for a particular material, it has, process parameters already set into it, which was almost like each company has worked for more than 5 to 10 years to optimize for that particular material. So that's why that license becomes so costly. But as a researchers, we need to understand what is happening in the background. Okay, so though this statement looks beautiful, but when we start depositing, I mean, like, it doesn't break the limits of manufacturability, but it breaks our imaginations. So that is what we have slowly realized. Now, quickly going into an overview of metal additive manufacturing. I'm sticking myself to metal. Okay, and slowly we will see that we will be boiling down to only one process. So I'm not just going through this definition, but typically if you go back into books in the 2010 or 11, so typically this is a joining process or a welding process where you fuse one layer over the other, or you weld deposit one layer over the other, and typically it is a bottom up approach. Now within the metal additive manufacturing process, if you try to see what are the two common processes. So I'm just following the IITM standard only, because nowadays there are a lot of other manufacturing processes like ultrasonic assisted, solid state additive manufacturing. So all these are also dealing with metals, but I'm just following the IITM standard. So then you can subclassify them into powder bed fusion, also called as selective laser melting, direct metal laser sintering. But all these are commercial names of a particular company. Okay, so but the scientific name would be simply powder bed fusion process. The other one is the directed energy deposition process. Both of them have their own importance in the field of manufacturing, and both of them have their own limitations. We will try to see them. So in both of these cases, like I said, we are dealing with the metal, which essentially means we need temperatures of the order of 700 degrees centigrade to 300 degrees centigrade. So these are the temperatures we are targeting, because most of the metals fall within this category. So we need certain energy sources for melting these particular materials. So the most commonly used energy beams, I mean, like, we are subclassifying each one of them, are laser beam and electron beam. When it comes to directed energy deposition, we are also using electric arc. I mean, like, our typical arc welding processes. Any arc welding processes can be used for additive manufacturing in directed energy deposition category. So as far as this particular talk is concerned, we will stick to laser beam, electric arc, and directed energy deposition. This is the combination to which we will try to stick. But it is always important to understand what are the limitations of these two particular processes. Now, in a broader way, I mean, like, I just kept it in a very simplistic manner. This is the powder bed fusion process, and you can see there is a laser and then there is a scanning laser. So all of us know there is a build platform. It will move down by a predefined thickness or a predefined displacement, and then from the feed container you will have the powder that is coming out of the feed container, metered quantity, what we call it as dose factor. Okay, so in order to uniformly spread the powder, let us say I require 5 grams of powder to uniformly cover this build platform. So typically I take 10 grams or 20 grams, because if you want to spread it uniformly, the dose factor should be slightly higher than the required quantity. So that much of dose factor or required quantity comes outside, and this scraper simply spreads the powder uniformly on the build platform, And using this scanning mirror, you are selectively melting the areas. So that is how the name came, selective laser melting. But we will stick to powder bed fusion only. So this is how a component is made in a powder bed fusion process. Now, let us assume one of the popular application or very wide used application in industries, refurbishment of worn out components. That also comes under additive manufacturing. Now, can we do refurbishment of components in powder bed fusion process? No, absolutely no, because here always we need a flat surface on which the laser will uh, scan and it will melt. But if you give any arbitrary structure on arbitrary shape, then it becomes very difficult for the powder bed fusion to repair that particular component. So that is where the laser directed energy deposition comes into picture. But remember, laser directed energy deposition can also refurbish a component as well as it can also generate a component. It can do both. But only thing is at the cost of precision or the quality of the surface. So typically in laser directed energy deposition, you will get poor surface finish. That is the only problem. And you have a number of solutions actually. You can go for laser surface polishing. So there are ways to overcome those. Apart from that, one basic difference we need to also identify between these two. I mean, like the reason why we are getting high precision here and why not here is because of the spot diameter we are selecting and the layer thickness. Here we typically select between 20 micron to maximum 80 or 100 micron. Even we don't touch 100. Most of the time we end up with 20 to 60 micrometer layer thickness only. And the spot diameter in the range of 70 to 100 micrometer. Whereas when it comes to this DED process, it will be in the range of 2 to 3 mm. Sometimes people use 1 mm, but this is not preferred because most of these lasers we are talking about all are fiber lasers. They have Gaussian intensity. So at 1 mm, this peak becomes quite significant, and it will start introducing keyholes and all those things. But because of this smaller spot diameter, the energy densities you achieve in powder bed fusion are quite high, and this is something which results in faster scanning of the laser and leading to the high cooling rates. So I will not go into effect of cooling rates right now. We will see it later. But in a simple way, we can say that higher the cooling rates, more refined will be the microstructure. It is good sometimes, it is bad sometimes. If too much of martensitic phase is forming, it is bad. If you are making a composite, if the cooling rate is too fast, then the metal matrix and the other composite material which you have mixed will not have any wettability. So there are advantages and disadvantages of this. So here in this case, you can see the energy densities are quite low compared to your powder bed fusion process, and cooling rates are also quite low. Okay, so this is basic difference. I don't say this is the only difference, but from the perspective of process parameters or the energy input, this is the basic difference. And then from the perspective of cooling rates, this is how they differ. Okay, now the next process what we have is the WAM, wire arc additive manufacturing, which is once again a very popular process. Nowadays, people are very interested in large area additive manufacturing or big area additive manufacturing, either LAM or BAM. Okay, so large area additive manufacturing or big area additive manufacturing. So if you are looking at these two areas, so one of the attractive process is the WAM process. It is just your GMAW or GTAW. So it's a welding torch, but it is integrated with the kinematic system in such a way that instead of simply depositing one bead of weld line, you can deposit couple of them one over the other. So for a simplistic way of understanding, I kept this one where you can see layer number 1, 2, 3, 4, 5, 6. So there are 6 weld beads which were laid one over the other. Okay, and then you were able to make this T section out of it. Like I said, the DED process has very high deposition rates, but has a very poor quality of surface finish. So it requires slightly, higher amount of, post processing. That is something which we cannot avoid, especially in case of VAM. It requires a lot of machining. At least in case of laser DED, it's not that much, but here it will be very high. Okay. So just for understanding, I kept, the scale of components that you can manufacture using this hierarchy additive manufacturing process. So here you can see it's, almost like 1.3 meter in diameter, a propeller. So the whole propeller can be made out of additive manufacturing process. Now, people may ask, like, like propeller is something which is existing from ages. Then, why do we want to do it VAM when the conventional processes are comfortably doing it from ages? True, but we need to understand that the amount of material we are wasting in case of conventional process, because it's a subtractive manufacturing process. You need to take a block of material, remove all the bulk material, and then come to this particular profile, which makes it, not an economical process. Also, the freedom in design or modification, because see, like I said, there are manufacturability limits. You cannot design any component and send it to the production floor. You need to understand the capability of your production floor. Now, but with this additive manufacturing process, if your process is very well optimized, you can create complex components. Like it essentially means you have freedom for design. So this is what we call it for design for manufacturing, DFM. Okay. So this is something which is changing the way we look at manufacturing sector. So these are the three processes, and now we need to understand the limitations of these three processes. Now this is something which I took it from a website from NASA. So they were trying to make these engines, which currently DRDO is also trying to do, and we are working on that one. Now, given the option, you have powder bed fusion, powder bed fusion process. You have LDED, then you have VAM process. So out of these, which one is best suited for this sort of engines? So you can see this particular whole engine component is made out of additive manufacturing. Now, which one will we prefer is a question. Now, if you see, if you look at most of these powder bed fusion systems, the build area is very much limited. You cannot, make such a big component in a, powder bed fusion process. Now, there are its own limitations because you are using a laser, and let us say this is the mirror. Laser falls here and it falls here. Instead of making it fall here, if you make it fall from this point to somewhere here, like assuming that I made my plate quite large, then the spot diameter what we will achieve at this point and this point will not be the same. Okay, it becomes more elliptical. So the bead characteristics or the deposition characteristics over here and over here doesn't match. This is something which is limiting the increase in size of this build volume. Now, are the people trying to increase its volume? Yes. Now, how are they doing it? So instead of having one laser inside your powder bed fusion system, you can right now you can get a laser system with powder bed system with 10 two lasers, and also there are quad laser systems. So as of now, we can see there are few companies which are producing with quad lasers, so that this issue of focusing the laser beam at a farther place is reduced. So for that they were using 4 lasers. So this is the limitation. So ultimately you can see right now we have only 2 options when we go to the large area additive manufacturing, that is DED and VAM. However, these components were made after years and years of research. Let us try to understand the complexities involved. So now we will try to understand the process. First, what we have seen is the basic introduction. Now we will try to understand LDED process or laser directed energy deposition process, and then we will go to the complexities of the process. I will try to keep it simple here. Just a minute. So this is how the process looks like. The step 1, give me a minute. So the step 1, you have a coaxial nozzle, you start feeding the powder through this particular nozzle. Okay. Now, if you see, compared to your VAM process or powder bed fusion process, here the powder is blowing or it is moving. So these dynamics of this particular powder makes this process much more complex. Here the powder is not stationary, rather you are blowing it. So since the powder flow is quite dynamic, you will see n number of problems in this process. Now let us try to see what happens in the next step. In the next step, you are going to switch on the laser. Now the powder material and the laser starts interacting with each other. Okay, so maybe typically 50% of the energy will be absorbed by the powder and the 50% passes through the powder and reaches to the substrate. Now, when will this occur? Now, let us say I keep my substrate over here, assume, because this is what we call it as standoff distance. Okay, I'm keeping my substrate over here. If you see within this location, okay, within this location, there is no interaction between the laser and the powder, which essentially means the whole laser energy will couple into the substrate. It will excessively melt the material or the substrate, but it will not result in any sort of good deposition. So this particular standoff distance will not work for you. Then the next option is keeping over here. Here you can see the laser is interacting with the powder and a good amount of laser is also coming into the substrate. This is something which we call it as an optimum zone. Okay, fine. Let me go over here. The problem here is two things. First thing, the amount of powder interaction with the laser increases. So the more and more amount of laser will be absorbed by the powder. And by the time the powder is reaching to the substrate, it is getting diverged. So you are no more in the powder converging zone, rather you went into diverging zone. So this will also result in excess dilution or improper depositions. So you can see from the just by this particular video, you can see standoff distance plays a very crucial role. Now, is this always bad or is this always bad? Definitely not. For real-time monitoring and especially for the controlling, you will see we will play or we will take the advantage of no deposition over here and melting. So I will show you that one as well, where you intentionally don't want to deposit, but you want to melt it. Parallelly, within the same deposition at preferable locations, you want to deposit it, but you don't want to excessively melt it. So we will try to exploit this particular physics in real-time deposition and controlling some of the geometrical aspects. Okay, so this is the basics of DED. Once this is done, you have decided where to keep your substrate. Just keep the substrate there, and then you can start depositing. Now, the wall you are seeing over here, which is getting deposited, this we have achieved after 1 month of trials and 1 month of thorough study on the process parameters and all those things. It just did not happen in a day. Okay, so this is the DED process. So typically in few statements, laser DED process is an additive manufacturing technique wherein the powder is fed through the nozzles. It can be lateral, it can be coaxial, it can be discrete. So there are n number of nozzles. So what we are using is a coaxial nozzle, and simultaneously the laser is fed from the center of the nozzle such that both of them interact and fuse onto the substrate. This is as simple as that in terms of statement. But as you look at the process, this is how it takes place. So this is laser DED process. So I mean, like, since it is an online program, I thought it would be good to keep the videos. So I have collected all these things, and then let us try to understand why laser material interaction is so important when it comes to additive manufacturing. It is also important in powder bed fusion, but I'm not touching it here. But in case of DED, let us try to understand what happens within our processing zone. Now, what we have is the laser energy coming in. Now, it starts getting distributed. How? Now let us assume some of the laser energy gets absorbed with the powder particles. Good. If the laser energy is getting absorbed in the powder particles, then it is good because its temperature keeps on rising by the time it reaches to the substrate, so it can readily get deposited. But do understand that in our previous this video, if you can see, I just forgot to mention that point. Just give me a minute. So now if you see over here, these two are more or less these videos were took at the same magnification. You see, this is the powder footprint diameter, something almost close to 10 mm. Okay. Whereas if you see the laser and material interaction footprint diameter, it is close to 2 mm or 3 mm, which essentially means the remaining powder in this 7 mm is not at all fusing. Okay, so this is what how we define catchment efficiency: the amount of powder fed to the amount of powder deposited. Now, so there are certain powder particles which absorb the laser energy, and but they don't participate in the deposition, so that energy is lost, right? And we are talking about laser. It's a light or a radiation, right? So every surface reflects laser beam by a different value. So some of the energy is lost by the reflection from the substrate. Some of the energy is lost by reflection from the powder particles. And also we have our regular losses like conduction, convection, radiation. They are anyhow there. So if you see, it's a quite complex process. So we need to understand, or we need to control what is the energy reaching to the substrate. Energy should reach to the substrate. I mean, like, we will see what happens if it doesn't reach to the substrate, or if it reaches in excess to the substrate. Now let us assume we have chosen our powder mass flow rate, okay, M, in such a way that the whole energy gets absorbed only in the powder. Very minimalistic amount is reaching to the substrate. Then what will happen? You will end up having boiling phenomenon, which essentially means if you want to deposit one more tracker over here, okay, then this is the shadowed region where there won't be any deposition taking place, and you will have interrun porosity. Okay, so the moment you have interrun porosity, that component will not have expected mechanical properties. So this is not good, which essentially means you need to control this energy that is going into the substrate. Now, it's not like just I will increase my laser power. It will not work, because your energy that is reaching to the substrate is not controlled by the power. Rather, it is controlled by the powder cloud density. So assume the sun, and there is a cloud over here, and you are standing over here. So the energy that, or the the radiation from the sun that reaches to you depends upon how denser is this cloud. So in our additive manufacturing, this is our substrate, this is our powder, and this is our laser. Now the energy reaching to the substrate depends upon the powder cloud density. It doesn't depend upon the laser power. Okay, I mean, like, when we talk about fraction, now you need to control this powder cloud density, which is quite dynamic because it is blowing, right? So now we will try to see how do we control that. Okay, once we understand how to control that, then we can go into real-time monitoring, because this is one of the important parameters when it comes to solving one of the major issue in additive manufacturing process. Now let us assume we have selected in such a way that the powder cloud density is quite low. Then what will happen? It will start burning you. If it is sun and then there are no clouds, we feel lot of heat and it starts burning the skin. The same thing happens to the substrate. So there will be excess dilution, minimum deposition. So there is an optimum zone in between this. So how do we achieve this? So in order to understand this, before studying the single bit tracks, we are supposed to study the powder stream characteristics. Okay. Now, when I say what powder stream characteristics, what are those? What is the distance from the nozzle tip at which your powder stream is focusing? And what is the footprint diameter at the focal point of this particular powder? I'm not talking about the focal point of laser. I'm talking about the focal point of powder. Now you see there are two focal points. One is focal point of laser. The second one is focal point of powder. Now, once you take this image and if you use this density based clustering technique, okay, density based clustering technique, okay, this is the complex name which I'm using, but if you want to do it simply, just open this image in Picasso, go to heat map, click on heat map, and you will get done. Okay, so the easiest way is that you go to Picasso, upload this image, just go to heat map, adjust brightness and contrast, and you will achieve this. But if you do it, if you want to do it in a much more scientific way, go to MATLAB, measure the intensity of each pixel, assign the ranges for each pixel intensity. From this range to this range is one color, from this range to this range. So the technique is density based clustering, but if you want to simply use it, you can go with heat maps. Okay, so this is a heat map. I did not do any this intensity based clustering, but just I used the Picasso software and I used heat map, and you can see what exactly I'm talking about. You look at the center of this particular powder stream, there is a hot zone or there is a dense zone. So laser is not switched on, by the way. So there is a dense zone. So now I need to control the density of the powder over here so that there will be decent amount of energy reaching to the substrate. Now, how will I do that? So this is how it looks like. Okay, the moment you switch on the laser, you see this is where the laser and powder are interacting, and they are dense, quite dense. Okay, now how do I control that? So that is the main question. So in order to take all these images, we did not use any complex experimental setup. What we have used is this 15-watt LED lights that we use for our false ceiling. We kept 3 of them, 2 from this side, 1 from the bottom. We tried to eliminate the powder particles because they are being, like the powders being metallic, they will shine. Then you just use any DSLR camera or any point and shoot camera from this side, and you can capture this powder stream. So this is how we have captured the powder stream, and then you can do all these studies using the Picasso software simply. Okay, but it is also important to understand how this heat map works, that is density based clustering. Now by doing that, we try to change carrier gas flow rate. What does this carrier gas flow rate dictate? It dictates the inertia or the kinetic energy that is provided to the particle. Okay, and then we also try to change powder mass flow rate. Okay, what is the amount of powder that is getting discharged? Now for a simple understanding, let us go to the higher values so that it is predominant, like it will be very significantly visible. Now if you see, when I'm using 50 gram per minute and I'm using 10 liter per minute, which essentially means minimum kinetic energy is provided. So this is the powder's footprint diameter. Now for the same mass flow rate of powder, I am using 40 liter per minute, means I imparted higher amount of kinetic energy. Then if you see, this footprint became quite small. Remember, the amount of powder available here and here, both are same, but the density, how tightly you are able to pack the material, depends upon your carrier gas flow rate. Now if you try to fire a laser now, in this case most of the energy will get blocked, so you may end up with balling. Here you may get an optimum deposition. So let us try to see what happens. So just remember this table, okay, this whole chart, and then you come to this one. So this is like complete process study what we were carrying out. So I did not take anything from the literature because we started from scratch. I thought I will represent the same. Now if you see, in all these cases you are ending up with balling phenomena. Let us assume 45 gram per minute over here and here, and 40 liter per minute over here. You see, slowly the intensity of this is also balling only. This is also not good actually, because you have too much of powder, so it's shielding completely the laser. So you are not having proper wetting. And Within this, if you try to see the balling over here and the balling over here, it is quite significantly visible over here. So none of these are parameters to be deposited. Okay. Now, parallelly, you come onto this direction where you are decreasing your carrier gas flow rate, sorry, powder mass flow rate, and you will see you are achieving good tracks over here, over here. Here you are having slightly higher amount of dilution. So this is having higher amount of dilution at 30 gram per minute. So what I try to do is I try to control my powder cloud density. Okay. The moment I try to compress it or increase the density, I was able to control my dilution. You see over here and over here, it's like here it is like 40% dilution, it is only like 15 or 20%. So I was able to reduce my dilution not by changing the laser power, not by changing the laser velocity or the spot diameter, which dictates the heat input. Rather, just by changing my carrier gas flow rate or powder cloud density, I'm able to control this. Also, parallelly, see my deposition has also increased. Okay. So by doing all this study, what we found out, like this is good, this is good, this deposition is good, this deposition is good. So this particular map makes you understand which one is good and which one is not good, right? So when I say which one is good, which one is not good, this is for deposition. But we will see when we try to control things in real time, this will also become good for correcting some errors. Okay. Just once again, just for your understanding, we try to represent in terms of what you say, numbers. Now if you see, this is, let us say, at 40 gram per minute, I started measuring my footprint diameter. Okay, so this is the footprint diameter of the powder at 40 gram per minute. If you see, at 40 liter per minute, I'm having the smallest footprint diameter possible, whereas at 10 liter per minute, my footprint is almost close to 5 mm. Okay, which essentially means the density of powder cloud is higher here, lesser here, and ultimately it will show its effect on the bead geometry. So here if you see, laser power, scan speed, spot diameter, all laser parameters are kept constant, but by just changing your carrier gas flow rate, you can see we were able to control the dilution. So we were controlling in such a way that slowly we are reaching to the balling phenomenon, right? So here you can see there is 50% dilution. Here you can see it is 10 to 15%, which is very good for additive manufacturing, right? So this is how your laser material interaction helps you in understanding which parameter to be selected, not in terms of power and velocity, but rather than carrier gas flow rate and powder mass flow rate. Then we were talking about the standoff distance. Now, what is the standoff distance doing? Now, here I have shown you 3 videos where we kept standoff distance 15, 20, and 25 mm, keeping all other process parameters constant. Now, if you see over here, at standoff distance 15 mm, excess dilution is there and there is no deposition at all. It is like dilution is 80% and then deposition is 20%, right? Whereas here it has a decent dilution of maybe 20 to 25, and then it has a very good bead geometry. Here it got further reduced, the dilution got further reduced, right? Now, what exactly is happening within this? Why is it so? Just by changing spot, like SOD. Already I have explained in our introduction slide, but for a better understanding, let us try to see in terms of schematic. Let me have all the 3 figures. Now, if you see, this is at 15 mm SOD, this is at 20 mm SOD, this is at 25 mm SOD. Now, what is happening in each of these cases? Remember, in all these cases, our spot diameter, laser spot diameter on the substrate is kept constant. Okay, that is not varying. Now, then what exactly is happening here? So, if you see at 15 mm SOD, the powder is not at all interacting with this, laser. I mean, like, because its converging point is somewhere here, and you kept your SOD here. So, the powder cloud density is quite less, so most of the energy is getting coupled to the substrate and you have excess dilution. Whereas when you keep the powder focal point on the substrate surface, that is something which we call it as an optimum one. Okay, so using that we are getting this one. But if the powder focal point is kept above the substrate surface, then the cloud density in terms of its length will also increase. So the energy reaching to the substrate will decrease. So that is what we are experiencing here. So there is no dilution because energy is not reaching to the substrate. But still, in this particular condition, we are in a good state. Okay, this is also a good bit. But only thing is, if this is not properly controlled, then you will end up with balling. Okay, so that is what we tried to show it over here. How this SOD and the laser material interaction, affects your bead geometry. So this is the effect of standoff distance, and I will show you how we can exploit this as an advantage in case of deposition. Okay. Now the other one is the laser spot diameter, which is least varied in additive manufacturing. Once again, it can be powder bed fusion or it can be in DED process. This is something which people really don't want to change it. Now, fine, you don't change it, but how do you decide what is optimum? Typically, if you see all our depositions we do at 2.2 mm, but how did we achieve this? Okay, this was not achieved based on the powder footprint, definitely not. Okay, now let us assume the red color one is the spot diameter, laser spot diameter, and the outer periphery dotted line, black colored one, is the powder footprint. 99.9% of the times you fall in this range only, which essentially means always your spot diameter is lesser than the footprint diameter. Okay, and you can also try to achieve this, but in order to achieve this, we have seen our footprint diameter goes up to 5 mm. So larger spot diameters need to be used. Larger the spot diameter, larger the bead width will be. But let us assume I want to deposit a 1 mm thin wall. Then none of these cases will work because your design is controlling what you want, what is the spot diameter you want. Okay, so these are the three conditions which are possible. That is powder footprint bigger than laser spot diameter, or laser spot diameter equal to the powder footprint, or laser spot diameter higher than this. But the only problem we need to understand with increasing the laser spot diameter is these are Gaussian beams. Okay, now how does this Gaussian beams going to affect? So now if you see, assume that this is the threshold energy that is required to melt the material. Okay, so now as you start increasing the beam diameter, so this is like somewhere here, this is the beam diameter, and this is somewhere here, and this is at the focal point. Now if you see, whenever you are increasing the beam diameter, because of this Gaussian nature, the amount of energy you have above the threshold value is this much only. You calculate the area, you will understand what is the value. But at a smaller spot diameter, this is the energy above threshold value, whereas here it is this much. So if you are varying the spot diameter, you should be extremely careful, otherwise you will fall into this zone. Now you can say that, okay, I will pump higher amount of energy so that this will slightly go up. Yes, you can increase your laser power, but it has its own disadvantages. What are those? If you try to increase the laser power, the energy below the threshold is typically consumed in preheating the substrate or creating what we call it as heat affected zone. Now that also keeps on increasing. So that's why we typically stick to 2.2 mm, which is an optimum one. Below that we will have dilution, above that you will have heat affected zone. Okay, so optimizing spot diameter is not that easy, but the physics behind hello.
Yeah, sorry, some disturbance.
Yeah, sure, fine. Now into real-time monitoring and the challenges in additive manufacturing. I will just touch one of the challenge, which to date is a hot topic. You go to any industry, not in India, around across the world, this is the major problem, including the industry I'm talking about. I mean, like you would see whenever someone comes to sell the equipment like for DED processes, okay, they will show you beautiful pictures of complex components deposited using DED. Okay, I'm not talking about powder bed fusion process. It has a different window of operation, but DED process I'm talking about. They will come up with almost like 6 feet component on their presentations, and it takes months, altogether months, like 6 months, 8 months to deposit that component. Why? If you try to probe them, like what is the procedure they have followed to deposit that, they deposit one layer, wait for 10 to 20 minutes, let it cool, then deposit the next layer. This is what most of the industries were doing. I mean, like, who sell these components, I mean, like DD setup for us. So just to attract, they will show you a large component, and we assume that okay, this I can deposit using this. We buy it and we end up with a chunk of molten pool, nothing more than that. Okay, because the procedure what they have followed, they don't really disclose, unless otherwise you keep on asking them. Now what is the problem? So this is the substrate, and on that substrate you have deposited your first bead. Okay, in case of additive manufacturing, your substrate acts as something called as heat sink, which essentially means whenever you deposit the weld bead. Okay, I'm talking about weld bead because that is how a fundamental definition of additive has started. Now you have thousands of definitions, but let me say that when you deposit the first bead, okay, so the immediately heat will be conducted into the substrate quite comfortably, and it will cool down quickly. Now remember, the profile the bead takes depends upon what is the cooling rate. Okay, if cooling rate is too high, it will simply become like a ball. So you need to have a moderate one so that you will get a bead. So let us assume you are getting a proper bead. Good, very good. Then you started depositing layers one after the other. So as you keep moving in the z direction, your distance of the deposited bead from your heat sink, let us don't call it as substrate, the distance from the heat sink increases. And you see here, it is a three-dimensional heat conduction. I mean, like, it is conducting the heat in every possible direction like this. But here what happens, it can only conduct the heat laterally, sorry, radially downwards. But laterally it cannot conduct any heat, because all that it can do is like convection over here. It cannot conduct, which essentially means as the layer number is increasing, more and more amount of heat is getting accumulated. This is something which is the major cause which is creating all sort of problems in additive manufacturing, whether it is powder bed fusion, whether it is laser DED, or whether it is VAM. People use, in case of VAM, it is slightly easy to control this, because you can use a gas jet, you can use a mist and all those things. But when you are blowing the powder, you cannot use all these things, because parallelly the powder will also get blown away. Okay, so indeed it is much more complex to control this. Now, because of this heat accumulation, there are several things happening. What are those? First one, because of this heat accumulation, the thermal cycle of the molten pool over here is different, which essentially means the cooling rate. Now, all of us know the mechanical property of a particular component is dictated by its microstructure, which is controlled by TTT curve, time temperature transformation curve. And now, in casting and other conventional manufacturing processes, the whole components undergoes same type of time temperature transformation curve. But in this case, the layer 1 has a different TTT curve, the layer N has a different TTT curve, which essentially means the structure over here and the structure or the microstructure over here is not same. So you have an anisotropy in terms of microstructure introduced into your component. So this is the first one problem. Okay, this inhomogeneous microstructure introduces anisotropy into your additively manufactured component. Point one. Point two, like I said, the way the bead gets wetted onto the substrate depends upon its molten pool lifetime or the temperature gradient. if the temperature gradient is very low, the same bead which we have deposited in the first layer, when it comes to the nth layer, it will start spreading like this. It will overflow. Okay. So, which essentially means as the wall keeps on depositing, it becomes wider and wider and wider, and you will have a teardrop shape. This is what you will end up with if you don't control the process parameters properly. Okay. So, you will have a teardrop rather than a rectangular wall. Okay. This is the next challenge in terms of geometry. Third challenge is this molten pool becomes unstable, creating waviness on the surface. Okay. Now let us try to see all these challenges. Okay. When the actual component is getting deposited. So here you see when the deposition is taking place for the first few layers, there was no waviness. But as the component is getting deposited, you will see the waviness is getting introduced because now the molten pool is size is increasing and it's getting accumulated, heat is getting accumulated, because of which heat accumulation, the molten pool size increases. Also, it becomes unstable, introducing this sort of waviness. You see, complete the surface is wavy. So, this is the first, challenge in additive manufacturing to control the waviness. The second one is heat accumulation. You see, when it is depositing, it becomes, by the time it reaches over here, the whole component will become red hot. Okay. Just give me a minute. So by the time it reaches to this end of deposition, you will see the whole component is becoming red hot, which essentially means all the properties of this particular shaft got changed. Okay, complete recrystallization or phase transformation occurs in the whole shaft, which is not at all good. This is not something which we are supposed to do. Then it is about thick sections. Now let us go to thin sections and see what happens. Sorry. Okay. When it comes to depositions on a thin sections, so you are depositing very well. When you are depositing on thick section, it is depositing very well. Now just see what happens when it came to the thin section because of heat accumulation. It's gone, because here you are giving the heat radially, and remember there is no substrate below this which can conduct heat. Rather it's like in air. So the whole heat is getting entrapped into it. So this heat accumulation is simply breaking your component. But remember, this parameter is not a parameter for laser cutting. This is just simply for deposition, but it is doing cutting. Okay, which essentially means you can understand the sort of problems this heat accumulation creates. Okay, so just out of that video, I have taken few screenshots. Just give me a minute. And here you can see this is the molten pool size, or the red hot zone. Let me not call as molten pool, red hot zone size when it comes to the layer 3. And the same thing when it comes to layer 39. You see, this became from this to somewhere here. So you can understand how unstable the molten pool will become. Okay, here if you see, the surface is smooth, but as you come over here, you can see that waviness has started. This was only up to 39 layers. Like as we went up, we have observed that it completely became uneven. Okay, now the same thing happens in the VAM process also. Just the same thing happens in the VAM process. So this is the arc deposition technique where we are trying to deposit layer, and this is the layer 2. Okay, so here we have used some thermal imaging camera, but typically I prefer to use pyrometer. So here you can see this one, and when it comes to layer 12, you see the size of the molten pool has drastically increased compared to this one. So that is something which creates uniform geometry. Okay, now with this background about additive manufacturing, laser material interaction, and then challenges in additive manufacturing, we will try to jump into monitoring of molten pool thermal history. Now, why molten pool thermal history? because we have seen most of the challenges are related with controlling the thermal history of the molten pool. So that's why we strike forward trying to monitor the molten pool thermal history. Now, is it so easy? No, because when you want to monitor this molten pool thermal history, especially in laser, do remember our cooling rates of are the order of 10 to the power of 3 to 10 to the power of 6. That is what my second slide says. Now, why was that kept? Because your thermocouple will not work in this case. First thing we need to understand, if you want to monitor the temperatures in laser-based additive manufacturing, thermocouple works at 10 Hz frequency, whereas your cooling rates are of the order of 1 kilohertz, right? 10 to the power of 3 to 10 to the power of 6. So it won't be able to, measure the thermal history properly. So you need some sort of non-contact type fast, sensors. Now, how do you select this? That is the million dollar question, because it's not like you go to a store and you buy it. In order to select a particular what you call it as detector, you need to first understand that every element or every object in the universe emits radiation. This is something which we know, but the wavelength at which it emits depends upon its temperature. Now, if you see during the COVID times, in every shopping mall or in every place you have this thermal imaging cameras or this thermal guns, handheld thermal guns. How do they work? They were operating at a particular wavelength where the intensity is assumed to be high. Now, let us assume you see this curve. Just I have used these equations from the Planck's law and then I have plotted this one. If you see at 3, sorry, just take my pointer. Now, if you see, if your molten pool temperature is 3000 Kelvin, then at if you measure the 1 micrometer wavelength, you will have higher intensities. So your detector should be able to measure 1 micrometer wavelength. But typically, in case of metals, we target from, let us say, 750 to 2000 degrees centigrade. Now, if you use this one, then which one is good? Obviously, if you see over here, okay, this one at 1.6 micrometer wavelength, the intensity is high. So I am selecting my sensor at 1.6 micrometer. Now the next obvious question is, instead of this, I could have selected this one because the intensity is much more higher, that is 1 micrometer. Now the selection of this particular detectors not only depends upon the temperature, but what is the energy source you are using. I am using a laser. So the fiber laser has 1.06 micrometer wavelength, which essentially means if I select a detector which operates at 1 micrometer, it will not measure my temperature. Rather than that, it will start detecting my laser radiation. Okay. So you have to be extremely careful when you are dealing with the radiations or the beams. Okay. So your detector should be far away from the operating wavelength of the laser. But if you are using an arc, then you can obviously take 1 micrometer comfortably, you can take it. But if you are using a laser, since the wavelengths are very close, you are not supposed to take this. Rather, I will go to 1.6 micrometer wavelength. Now, will that stop my laser radiation from reaching the detector? Definitely no, because when we say optics, every optical component has its own threshold. Let us assume, nowadays you see the advertisements of some cement companies like Ambuja, something like that. Okay, they say that no thief can break that wall. It's true. Obviously, it is true. They are so strong, but that doesn't mean a bulldozer cannot break that wall. Okay, bulldozer will break it. Similarly, whenever an optical component has been designed and manufactured, it has a threshold. So though it operates at 1.6 micrometer, but if you try to use 1 watt or 2 watt or 10 watts of laser beam on those optics, it will pass through it because it cannot handle higher energy beams. Okay, so you need somehow you need to block this laser radiation reaching to the detector. How do you do that? You use something called as notch filters. Okay, so now if you see this notch filter, it will allow all the radiation except something from maybe roughly I can say 1050 to 1100 nanometer, which essentially means our 1060 nanometer is completely blocked. Okay, so these are what we call it as filters. And whenever you are using lasers and some sort of detectors, always you are supposed to use detectors. Otherwise, you will end up measuring the laser radiation rather than the multiple radiation. Parallelly, you also have band pass filters that also you can use, which will allow only 1600 nanometer. This one, that also you can use. So you need to choose between notch filter and band pass filters. Now we assume, fine, you got notch filter, you got band pass filter, you got the detector, and you targeted working on aluminum, and all of a sudden you got a project and you started working on steels or nickel based superalloy. Now previously the pyrometer range is, let us say, 0 degrees centigrade to 1000 degrees centigrade. Okay, measuring range. But now because of my change in material, I want to measure up to 2000. Then how do you do that? Simple. You use neutral density filters. What does they do? These are just like our sunglasses. Okay, they will cut the radiation. So by using this neutral density filters, you can play with the range of temperature that you can operate with your detector. Okay, so the same detector D, with the help of filters, which are notch filter, band pass filter, and neutral density filter. The same detector can be used for any sort of thermal application, but for this you need to understand these optics and these characteristics. Okay, so the first step in real-time monitoring is selection of detector. It can be a pyrometer, it can be a thermal imaging camera. Okay, the first step would be in real-time monitoring, selecting the wavelength at which you want your detector to work, then selecting the filters to block the radiation, then control the intensity by using the neutral density filters. So this is the first step in real-time monitoring. Okay, then once everything is done, so now you have a detector. On that detector you are adopting a particular filter, which essentially means the calibration is gone. No more the detector is calibrated. Now we cannot have black body with every one of us. It's quite costly, right? So how do you calibrate that? So the simplest way is take a copper die with a blind hole. Okay, fill this copper die with the material of your interest, for which you know the melting point. Use the laser beam, melt this whole material and allow it to solidify and record the thermal cycle. Then you know latent heat of solidification. So that is something where when you heat the temperature goes up, and when it solidifies, when it starts touching your solidification temperature. Okay, so then it will show a curve like this, where latent heat of solidification is getting released, and then it will fall. So from this you know the solidus temperature and you know the liquidus temperature. And for the selected material you already know both of them, right? So you know these points experimentally, and you know these points prior to that, and then use a calibration factor such that you will be restoring these to true temperatures. Okay, so this is how you calibrate the next step. Okay, this is one way of calibrating. The other way is you heat that material, take your pyrometer there, set emissivity at different values. I mean, like you, let us say I'm keeping a thermocouple over here, measuring its temperature. Okay, and parallelly I focus my sensor over here, measuring its temperature. Here I am supposed to set the emissivity value. Okay, so I will keep on changing my emissivity value. The next step is calculating the emissivity. Once the calibration is done, you need to calculate the emissivity. Now how do you do the emissivity calculation? Once again, I don't have black body. So I heat my substrate. It can be copper, stainless steel, Inconel, whatever you want to do. Heat it, measure the temperature using the thermocouple, which gives the true temperature. And then in your detector, keep changing your emissivity such that these two match with each other. Okay, these two should match. So the next step in real-time monitoring is calibrating your device, which is very important. Okay, it takes time. I mean, like, it's not that simple like what I have explained in one slide. It takes time. So here you can see this is the additive manufacturing nozzle we are using, and we are using a couple of IR pyrometers, which are non-contact type, just like your thermal guns. But here these can measure from 385 to 1650. But like I said, by using certain number of filters, I can always play with this range, recalibrate it, reuse it, okay, for any kind of material. That is something which you can do. Now we are done with the next step, second step. Then the third step is actually looking into the process. Okay, so here you can see, just give me a minute. Here you can see as the laser interacts with the powder, okay, the powder starts melting. So this is the heating cycle. So during this whole process, this is what happening. The temperature is rising up, rising up, rising up, and it reaches to this particular position. And then once the laser passes from that location, like here you see, it starts solidification, which essentially means cooling. So this is the cooling cycle. Now we will see why these are important for us. And once this cooling cycle is, you have this thermal cycle. This is the heating cycle. This is the cooling cycle. From here to here is the molten pool lifetime. From here to here is the solidification lifetime. All these things you can determine, because simply we know how a thermal cycle looks like, and you can determine each and every parameter. Now, what are we supposed to monitor? First thing, I mean, like, you have detector, you have calibrated it, you know what is happening in the process. Now, are you going to monitor the peak temperature? Most of the studies you will see people are monitoring peak temperature, but you need to understand this equation, simple equation. I don't want to make it complicated. Q equal to mCp delta T. And people say that, yes, if my Q increases, my delta T or the temperature of the substrate or the surface increases. Exactly true. But when it comes to additive manufacturing, you should remember that our catchment efficiency is not 100%. Typically, it is in 20 to 30%, which essentially means if I blow 100 grams of powder, only 20 to 30 grams is getting deposited, and the rest is just coming outside. It's not getting deposited, which essentially means my M is not constant over here. So if I keep on increasing my Q value, instead of delta T getting increased, your amount of powder catchment efficiency increases. Why is it so? For a, let us say, some amount of Q, this is the molten pool you have. Okay. Now you have increased to Q2, which is greater than Q1. Then obviously this molten pool size will increase. The moment molten pool size increases, you understand that our spot diameter is only 2.2 mm, whereas my footprint diameter of powder is 5 mm. So more amount of powder comes into picture. It gets, catchment efficiency goes up, which essentially means delta T is not going up. Your M is going up, which essentially once again means you will not observe any change in the temperature. This is the major problem. If you try to monitor the peak temperature, it's not a solid state welding process, okay, where the temperature varies. It will not vary. Rather than that, your mass will keep on varying. So monitoring delta T or the rising temperature or the peak temperature will not help you out. Rarely there is a proof. Yes, if you see it over here in this graph, we have changed the laser power from 600 watt to 1600 watt, which is almost like 3 times. We have increased the input energy, and you look at the peak temperature. It's always close to 2000, 2100. It's not even changing by 10 degree, 20 degree also, right? Which essentially means there is no point in measuring the peak temperature, but people do it. But still, this is what our experiments show. Then what are you going to do? If the peak temperature, so the you know the process, you know the detector, you know the filters to use. Now which parameter to be monitored? So we are at this stage where we need to decide which parameter. So the parameter should show significant difference with respect to the changes in the process. So this is where we identified that cooling rate is one such parameter, because if you see, when we are talking about layer by layer depositions, as I said, as the layer number increases, heat accumulation takes place. So this heat accumulation does not reflect in terms of peak temperature, but it can be easily captured using cooling rate, delta T by delta T. Now, how do you measure the cooling rate in real time? That is the one more big challenge. So that is where we come up with a unique solution which was patented actually. What we have done is we took two pyrometers, like what I have shown in our experimental set. Okay, one pyrometer is getting focused at the center of the molten pool. The other one is outside the molten pool and at the periphery where it can detect the temperature. Okay. Now what we are doing is, from the pyrometers what we get is voltage 1 and voltage, because all these are electrical devices. What you get is voltage, not the temperature. We convert it later. So I know the temperature at the center, I know the temperature at the periphery, which gives me delta T, and I know what is my scan velocity V. Okay, and I know what is the distance between these 2 points, that is D. So velocity equal to distance by time. So if I want to calculate time, it is distance by velocity. So I also know delta T, that is the difference between the time instances of these two. So if I subtract these voltages, divide it by the time depending upon the velocity and the spot diameter or the distance between these two diameters, I will be able to get the cooling rates in real time. Okay, so the next step is to identify the parameter which you want to measure. Okay, so now let us see whatever I said, is it true or false? Okay, so these are the parameters, 300 mm per minute to 1200 mm per minute. We try to monitor the peak temperature, and you see the peak temperature is more or less constant in all these cases. And what is the line energy? Line energy is laser power divided by scan speed. So now let us assume this is unit, or this is something like 1000 watt I have used. This is, in this case, it is 1000 by 300, the first case. In the last case, it is 1000 by 1200. Now you can see that this one is much higher than this value, line energy. And even after that much increase in the line energy, you see there is no change in the peak temperature. But by using this technique, when we started measuring the cooling rates for the same process parameters, okay, now you see in case of 1200 mm per minute, where the cooling rate is expected to be very high because the interaction times are less, you see this is the value of cooling rate, that is something close to 2800 degrees centigrade per second. When it comes to 300 mm per minute lower scan speed, you can see this is 750 close to degrees centigrade per second. So now you see the difference what you are able to detect. So the parameter which you select should be in a position to capture any sort of fluctuations in the process. So peak temperature will not work for that. Okay. So obviously you need to detect the cooling rates. Fine, I'm done. I have determined this is my cooling rate within which I want to operate. But how do you define, or how do you determine that the range of cooling rate within which you want to operate? Okay, so this is once again the same example, the real-time data I'm trying to show you. So you can see the peak temperature is not changing. Okay, also the tailing temperature, because of heat accumulation, it is slowly going up. And when you calculate the cooling rate with layer number, it decreases. Okay, now all this is good, but how do you determine? Because see, for let us say you have phase diagrams for conventional processes, but for additive manufacturing, how are you going to do that? So you need to determine, okay, this is the cooling rate within which my process needs to operate. But how do you know which type of cooling rate is going to give which type of structure? So the next step would be to develop process map. Unless otherwise you have a process map, you won't know at what cooling rate you need to operate so that you can control your scan speed or power to control the cooling rate. So we just looked at, I'm just quickly going to the process map. We tried to look at the cooling rates, okay, and we tried to look at the corresponding microstructures. This is Inconel 719 by the way. And if you see, when we are doing the remelting process, if the cooling rate is below 1250 degrees centigrade per second, you will typically end up with having equiaxial grains. If it is above 1600 degrees centigrade per second, you will be having columnar or columnar structure. Okay. But if you are in between these two, you will have a mixed stellar and equiaxial structure. Now, I know how to detect my cooling rates in real time using dual pyrometer. And I also know what is the structure I want, whether I want columnar structure. If it is a uniaxial loading component, columnar structure is good. If it is a biaxial loading component, this equiaxial structure is good. So I know my loading condition or real application. So based on that, I know what should be the microstructure, and from this process map you can pick which kind of zone you want to operate. And using your real-time detection technique, you can control your scan speeds or determine the scan speed such that you will always fall into this zone only. Okay. Now we are one step greedy. So if you see, each pyrometer comes or costs you around 1 lakh, and then the filter costs you around 30,000, right? So it's like almost like 1.5 lakhs of business to buy a pyrometer, which is really expensive, and we are using 2 of them. So the next step, what we try to do is, okay, can I reduce 2 pyrometers to 1 pyrometer? Is there any way? That is where we started scanning over the molten pool. This is, concept only. I mean, like the way you want to scan can change from person to person. Being mechanical engineering, I don't know much about electrical motors and everything. So what we simply did is, we took a stepper motor, we took a linear stage, and we wrote a simple program on an Arduino board such that this will oscillate. Now, by oscillating this, what we are doing actually, if this is your molten pool, okay, we are tracing the temperature from this point to this point at the tailing end of the or the red hot zone. Okay, so we are oscillating to and fro, and we are actually tracing the temperature using a single pyrometer only. And now just apply a few algorithms where you will measure the peak temperature, the lowest temperature, you subtract them, and you know what is the frequency at which this is scanning. So from that you can determine that time, delta t, and delta time, time difference. And then now using this particular technique, you are in a very good position to determine the cooling rate in real time. Okay, but you can replace this motor with several other things. Like I said, being mechanical, this is what I could thought of. So this is what we did, and we were able to determine using single pyrometer. We were able to continuously monitor the thermal history of the pyrometer. Okay, we did not use any thermal imaging cameras because that costs you around 40 to 50 lakhs, whereas this comes for only 1 lakh, and both of them more or less give you similar data. Okay, so this is the next technique. One is the dual pyrometer technique, which we have already patented. This is the next one, which we are at to file it. Okay, so this is the next technique. Done. Okay, we were talking about microstructure. Very good. We are able to keep it in control. But what happens to the waviness that is occurring because of heat accumulation? That is the next step. With this particular topic, I will stop. Okay, because of time. Now, once again, what we are trying to do, same. We are trying to monitor using this pyrometer. We are monitoring the temperature always on the substrate surface. I mean, like we are tempering effect, whereas the other pyrometer is mounted on a Z table.
Hello. Dr. Gopinath?
Okay, so just
sorry, Dr. Gopinath, we lost you actually, maybe last 1 minute, like not a minute, maybe 2 or 3 sentences we did not hear actually.
From this slide?
Yes, yeah, from here.
Yes. So actually our fiber network got damaged. So we were connecting from mobile, and then, continuously calls are coming.
Oh,
That's
okay. Okay, thank you.
Yeah. So we will start from this one. What was this topic? Yeah, waviness. Okay. Microfactory is done. We developed the process map. We developed the real-time monitoring technique to determine the cooling rates, and now we know how to control it. Now, waviness, how do you control this? This is the next question. Now, if you look at this particular setup, one pyrometer is continuously looking at the layer 1. It will keep on monitoring the first layer only, which essentially means the tempering cycles. The second one is mounted on a jet table, and it was given increment after each layer by a value of layer thickness. So the jet height will be increased for each layer by a value of layer thickness. Now, why this is important? Now, let us see. Sorry, give me a minute. Now, this curve, what you are showing, you are seeing here, the first one. This is it is unable to drop down to the room temperature or the minimum detectable temperature.
Sorry, Gopinath, again we lost you. Can you explain the graphs again? Sorry for that.
Yeah, sure. Yeah, sure. Now, okay. Now, this is the one which is detecting the temperature of every layer being deposited. This is something which is detecting the temperature of the first layer continuously. And if you see, this is the layer 1, layer 2, layer 3, increasing. The temperature of the first layer also has got saturated over something like 600 or 700 degrees centigrade because heat got accumulated. Now we know this heat accumulation molten pool, and this unstable molten pool results in what we call it as waviness. So you are gone. Okay, this is almost like 80 layers, and you see we are unable to deposit 3 centimeters of wall. I mean, like by the time we reach 3 centimeters, this is our condition. And remember, this is a 1 mm thin wall. If someone is talking about 10 mm thick wall, we will be able to comfortably deposit it. Okay, this is not a challenge. The challenge is depositing a thin wall of 1 mm. And you see, this heat accumulation is resulting in waviness. Then how do we control this? This is the next question. Okay, now by looking at this real-time data, we know that this is what heat accumulation is taking place. Corresponding to this heat accumulation, I can decrease my Q input. How do I do that? Either I decrease my laser power or increase my velocity. By doing these two things, I can do this. So the first step what we adopted is doing the same. By the way, here we are doing it manually because, once again, when I say PID controller, it's a black box, at least to me. So we were currently doing it manually. Maybe with the time, if some good student comes who has a good knowledge of PID, we will make it automatic. Then what we tried to do is we started looking at this heat accumulation cycles, and looking at that, we tried to maintain this temperature always constant. Like once the cycle one layer is deposited, it is expected to again fall back to the minimum detectable temperature. That is our target. So whenever we are detecting that, okay, my minimal detectable temperature, it is unable to reach, then what I am doing, immediately I am changing my velocity by a 50 mm per second, sorry, 50 mm per minute. So which essentially means from layer 1 to this layers, I'm continuously increasing my velocity to reduce my Q heat input. Now this is the 80 layered wall without any such sort of control or monitoring, and the same wall which the technique which we have adopted, you can see it over here, right? Definitely there is a huge difference. Don't say this is a groundbreaking, result, but still you can see there is a definitely lot of improvement. Now, if you keep on increasing the velocity, you will reach to a point where there won't be any deposition. Now, if you don't change the velocity, then you will set there is onset and its onset of wavelength, and it will keep on increasing. Again, you are in once again deadlock situation. You cannot increase the velocity anymore or reduce the power or energy anymore because there won't be any deposition. Then what are we going to do? This is where our laser material interaction comes into picture. If you remember, if the SOD is low, like 15 mm, the deposition is less. If the SOD is 20 mm, which is optimum, the deposition is high. Let us try to exploit this. So now what we try to do is, I know after a particular amount of deposition, I know there is waviness occurring. Now, if let us say this is like 2 mm in maybe the valley height is 2 mm. Now, what we are trying to do is we are trying to keep our powder focusing point over this point, which essentially means in this location it is in defocused condition. It is here in focused condition. So I'm changing my standoff distance. Once again, we did this manually, but I will tell you the technique to do in real time as well. So my powder is getting focused at the valley, and whereas at peak it is defocused. And by doing this, wherever it is defocused, there is no deposition. Wherever it is focused, there is huge amount of deposition, which essentially means the material deposited on the peak is very less, whereas on the valley is high. So if you do that for 2 or 3 times, you will be able to cover up these peaks. Okay, so this is like self-healing technique what we are adopting, and by using that technique or this material, this laser material interaction studies, so we started correcting it, and we went up to 212 layers, and we were comfortably able to build it up. We did not go further because these powder materials are expensive. I mean, like companies may deposit a component and display it for their use, but at R&D level, it becomes quite expensive. So, but up to 212 layers, you can see we were able to predominantly control this waviness. Forget about the error over here and over here or this one, because these are limitations from our CNCs. The CNCs which we use are typically not suitable for additive manufacturing. Since it is at R&D level, we did not focus much on CNC, but if you want to generate a component, then in fact your CNC plays a critical role, or the kinematic system. Okay, so this is something which we done manually once again. Okay, when you say control system, like I said, it's a black box to me. So what is the technique to do this particular monitoring in real time? Simple. You have these laser displacement sensors. These you will get for around 80,000. Okay, and they operate at 2 kilohertz, and their resolution will be up to 2 micrometers. Okay, so these sensors very small, and these are non-contact type sensors. You can comfortably use it. Just attach them to your nozzle, and you keep tracking the peaks and valleys height. Okay, and now typical control system. Once you have that one, you define lower control limit and upper control limit for this peak and valley distances. Now, any point of time, if it crosses the upper control limit, it gives you an alarm that, okay, waviness is going out of control. At that moment, what it will does is, it will try to bring down your Z value such that this powder focusing point will be at valley, and it will be defocused at the peak. So by adopting this particular technique, what you will do, if you deposit 2 or 3 layers, again, this you can bring it back to this condition where it is under control. Okay, so the technique is simple, but implementation part, you need a guy with who can do this control system and PID controllers and everything. Okay, so you can have this displacement sensor, attach it to your cladding head comfortably, and this can measure up to half a meter. Okay, the range will be around 500 mm. So which essentially means even if your nozzle is 300 mm length, you are attaching at the top of it still you have 200 mm measuring range with accuracy of 2 micrometer, which is more than enough, and it is 2 kilohertz. Let us not operate at 2 kilohertz. You can simply operate at something like 100 hertz is also very good enough. Okay, because if you have too much of data, computationally it will become heavy. You can operate at 100 hertz, use this particular technique, and control the waviness in real time. So we looked at the processes, we looked at laser material interaction in DED, we looked at the challenges, we looked at the techniques for real-time monitoring, or the unique techniques what you can adopt at a very cost-effective way. And then we also looked at how to control the microstructure, and now we looked at how to control the what you call it as waviness or the geometrical aspect. One last thing I will do is real-time detection of microstructure. Especially this is good for composites. Okay, composite means metal matrix composites. So like here, if you see, you have inconel plus 30% titanium carbide. Okay, you will get the desired property as long as titanium carbide is in its original form. I mean, like you have taken a randomly shaped particles. So this is the IN718 matrix. There should be a good wetting between the matrix and the particle. But remember, this should not get dissolved or dissociated and convert into dendrites like this. Okay. So if your molten pool lifetime is becoming too high, then this will start decomposing. I don't say melt, they start decomposing. Carbon is something which is notorious. It will immediately diffuse everywhere. Okay. And then it gets dissociated and it forms dendritic. And these dendrites are ceramic in nature, and you will lose the whole mechanical property. It makes it pretty. Okay. Now, how do you detect this? Okay. So that's what I kept the title, non-destructive way. So let us see how your real-time monitoring will help over here. Now, like I said, these are for different, lifetimes of molten pool or the cooling rates, whatever it is. These are all interrelated. Okay. So now if you see, when the molten pool lifetime is less than 0.45 seconds, you can see this is the TAC particle. A good amount of wetting is getting established. Okay. So here you can see it is much more visible, this shell core structure. So this is the shell core structure. So this is the shell, outer shell, which is lightish gray, and the inside core is black, which is titanium carbide, and the outside brighter region is IN718. But if the molten pool lifetime crosses 0.45 seconds, this will start dissociating into dendrites. And if you further keep on increasing the molten pool lifetime, you will end up with complete dendrites. Now, how do you detect this in real time? What is happening inside the molten pool? Even if you want to stop the process because this dissociation is taking place, how do you do that? Right? Now, we all know that in Conel 718, if the titanium carbide particle is not dissociating, then the metal matrix composite also shows the solidification self at the same location as that of Inconel 718. So this is the metal matrix red color. Am I audible? Hello?
Yes, you are audible.
Okay.
Yes.
So the red colored one is the metal matrix composite, that is IN718 and titanium carbide. The green color one is Inconel 718. So when I am processing below 0.45 seconds, that is at 1200 mm per minute higher scan speed, you can see that, okay, the solidification self of both the materials are happening at the same location. But at 400 mm, so at 400 mm per minute, if you see where the molten pool lifetime is greater than 0.45 seconds, the solidification self got shifted. Now, I mean, like if we remember the physical methodology, solidification self is dictated by the composition of the material. Now, any shift in solidification self location depicts or indicates that there is a compositional change, especially in this case, if the compositional change is occurring, which essentially means your titanium carbide is getting dissociated. That is what we have observed in our methods. If you see at a 1200 mm per minute, titanium carbide particles are intact. Okay, so the solidification self is occurring. I mean, like there is some amount of compositional change, but that would not significantly affect our solidification self location. It is same as Inconel 718, but at 400 mm per minute, you can see it got completely dendritic structure. And these images are at, by the way, same magnification. Okay, unfortunately, I did not keep the scale. Now, if you see, there is a complete compositional change, and that is getting depicted in terms of shift in solidification self. So, if you closely monitor your thermal history, you can also look at the microstructural changes in a non-destructive way instead of cutting and then polishing, keeping it in SCM. You can also judge that. Okay, but based on these results, you can always once again develop a process map. I mean, like once again, for every material you need to develop that process map. So this is the way we have developed the process map. Zone 1 results in porosity. Zone 2 is optimum 1. Zone 3 dissociation. Zone 4 excess dilution. Right? So this is how we have determined our zone. We now know the process map. We also know how to determine the cooling rate in real time. Now we also know how to control it. So once you do all these sort of steps for your particular material, you can develop a open closed loop control system for your particular material and additive manufacturing process. Okay, so with this, I would like to end my talk. Okay, so if there are any questions, I will be happy to answer them.
Thank you, Dr. Gopinath. It's a very thoughtful and insightful talk on real-time monitoring and control in additive manufacturing processes. And then we you covered in all maybe possible monitoring things. Okay, so really nice. Yeah, so now I request the participants to unmute yourself and ask your questions. And otherwise, even you can write it in the chat box also. I will take up the question.
Good morning, Dr. Gopinath, sir. This is Pramod, sir.
Yeah, good morning, Pramod. Yeah,
sir, yeah, it was a very nice presentation, sir. Thank you for clearing a lot of fundamentals for us. Sir, when you talked about the effect of standoff distance,
yes.
Sir, in that you said that you kept the laser beam diameter constant.
Yes.
So how was that achieved, sir? Because if you're moving the standoff distance focus, won't the beam diameter at the interaction point change, sir, like how you showed in the figures?
Yeah, sure. I will tell you. I mean, let me see. Let me go to the picture of how we are doing it. Okay, I think it is slightly below. Give me a minute. Okay, just a minute.
Yes.
I just want one picture so that you will get a gunshot answer for your question.
Yes, sir.
Yeah, this one. If you see here, the lens locations are not at same height. So what we do is, like, let us say I displace my laser head by 5 mm in Z direction. Okay, Z plus direction. Then I will move my lens down by 5 mm so that your focal point will be always at the same location. So the nozzle one which we have designed in 2012 in my MTech had that provision, and now if you buy from any company, they have introduced by this by default. Okay, so you can move the lens within your cladding head. That you can do.
Oh, okay.
So yeah. One is moving up, one is coming down.
Yeah. Okay. And sir, with respect to the example that you saw, that control in situ control of microstructure.
Yes.
Sir, in that, sir, if I can have a look at the graph. I'm sorry.
Okay. I mean, like, you are talking about Inconel or titanium carbide?
Sir, that Inconel titanium carbide that.
Oh, compound. Yeah. Just. This one, yeah.
Yes, sir. Yes. That shift, sir, that you showed in the solidus temperature. Sir, how were you able to determine that the solidus step was that the shift in that was the solidus temperature? So did you do any DEC calorimetry configuration or like based only
No,
on
no,
the
no, no, no.
temperature profile?
We did not do that. Okay, so that what you said is true. If you want to determine the absolute values, okay, that calorimetry needs to be done, but we don't really require that. All that we require is any shift in position from the expected value signifies that there is a change in the phase or the change in the composition. So that is where we have stopped it. We did not do any calorimetry or those techniques. Okay, DSC technique we did not adopt. So that is like that. See, what happens with that particular technique is it is very good technique to study the physics, but if the
Yes, sir.
same thing if you want to implement in real time, that technique will not work.
Okay.
And this is also what we have done here. If you see, this is molten pool lifetime. Once again, you cannot measure the molten pool lifetime. So what we did is we kept molten pool lifetime, okay, as a function of cooling rate. We generated an equation for this correlation between these two. See, because
Okay.
if the molten pool lifetime is high, cooling rate will be less. So this will be
Yes.
inversely proportional. Okay, so you can determine those type of equations, and then you determine the cooling rate, but you are estimating the molten pool lifetime, and then you control the process.
Yeah. Yes, sir. Yeah, that was all from my side. Thank you, sir. Thank you for such a wonderful presentation.
Yeah. Thank you. Thank you.
Yeah, thank you, Dr. Gopinath. So there is a question in chat box. I'll take it for you. How does titanium carbide in inconal matrix change into dendrites at lower temperatures?
Okay, so he might be asking about, he knows the melting point of the titanium carbide, which is like 2800 or something. I don't exactly remember the value, whereas here the value is 1810 only. So that's why I told, like, I did not use titanium carbide got melted. I used the term it got dissociated. Okay, so there is a difference between melting and dissociation. So it doesn't melt here, it gets dissociated. So if you keep this titanium carbide particle at elevated temperature for longer time, okay, and then this inconel 718, if you look at its chemical composition, it has niobium, molybdenum, as well as titanium, which are once again strong carbide formers. These dendrites are no more titanium carbide dendrites. These are a compound of niobium, molybdenum, and titanium carbide. Okay, so it doesn't melt, it just dissociates or dissolves. So the carbon can diffuse out. Okay, and that is how, in fact, your reaction layer is getting established. So I have some IITH images that I did not keep, but you will see this ring, outside ring is very rich in niobium, and this cell core structure is very important. Okay, so it doesn't melt, it just dissociates.
Okay.
I hope that answered his question.
Yes, yeah. Yeah, he said, okay, thank you. And then another question from Prathivi Rajan. He asked about how to get the pyrometer to focus exactly at melt pool.
True. So this pyrometer has an optics. So it's like a just it is a detector, and from your this particular molten pool, your IR radiation is coming like this. But how do you focus it onto the detector? So what we do is you keep a plano convex lens. Okay. Now the distance from this point to this point should be the focal length of the lens. Okay, but how do you identify this? For that, what this company does is it gave two diode lasers, one over here and one over on the other side. So these two focus at a one particular point, that is the focal length of that particular lens. So if you see it over here, you can see some small red dots. One dot corresponds to this one, the other dot corresponds to this one. So each pyrometer has two diodes on the along the diameter, and then both of them, whenever they are focused at a one particular point, it signifies that you are exactly at the focal length of that particular lens. So if you are not at that particular point, it will not give you any reading. Even if it varies by 5 mm, right? It will not give any reading. So this is used by using the guide lasers provided on this particular pyrometers.
Yeah. Thank you. So maybe you added a same. Is there any laser guides or optical guides to arrive at the exact position? So along with that question, he raised that this also. I hope you
Yes.
answered for that. Yeah.
Yeah, you can do that.
Fine. Yeah. Then next question from Deepak Kumar. He asked about. So he is interested in like work on composite. Okay, he is new to the field. Then he asked
Okay.
that how to proceed further.
Deepak, I can suggest you only one thing. See, laser can melt any sort of material. I mean, like, there is no doubt in that one. But if you are going for the hybrid ones, always remember you need spherical particles. That is the main challenge in this, DED process, because you have to blow the powder through the nozzle, and then it has to focus at a particular point. If the powder particles are not spherical, they don't focus. The first thing which you need to see is how close your powder particles to the circularity. Okay, that's first thing you need to do. The other one is you can, if you want to have a hybrid one, where want to composite, typically we go with pre-mixing of the powders in a metered quantity and then you blow them. Okay, so that is something which I can say as per your question. So I want to make a composite through additive manufacturing, then how will I proceed in this direction? Yeah, so whenever you make a composite, it can allow up to a certain composite percentage only. So you need to start with 10, 20, 30, 40, and beyond a certain value, you will see that there will be a lot of porosity and cracks. Okay, so that is something which will limit it. So I mean, like, this is something which we can tell to that question.
Yeah. Thank you. Yeah. So any other questions from participants? If no more questions, then I would like to thank Dr. Gopinath for sharing his research outputs with us. It's really great. We gotten a chance to understand about this process monitoring. I think in additive manufacturing, people are working on different domains, but this is a very interesting domain to explore a lot. So thanks for enlightening us in that particular topic. Okay, so yeah, thanks.